Okay, so homework 7 is posted, and it is more correlated data analysis. Two data sets, the exercise data and the cholesterol data, and I posted documentation for them on the discussion board. So see that to see what the variable names are and all that. For the cholesterol data, let me download them. Okay, so the first column is identifier. So that means, okay, so these data are organized in what we've been calling the wide format. So I talked about this in last night's Q&A some. Wide format means for longitudinal data like this, we have one individual per row, and all of the response values for that individual in multiple columns. So for these data, first column is treatment group. There's 2 treatments. Second column is ID. So that means that number 1 means that's the first individual in the treatment group 1. That's the second individual, and so on. And these are the 5 response values over time for the first individual in the first treatment group. So one detail that needs to be addressed is if we scroll down, we see the ID, the second column, is going 1, 2, 3, 4, ... And that's all for treatment group 1, column 1. If we scroll down, here's where treatment group 2 started, and the IDs started over at 1. So this is the first individual in the second comparison group, and so on. We don't want that. When we do regression, when we do GEE, we're going to pass in, we're going to say model the response as a function of treatment group, and we need to tell GEE what the identifier is for grouping observations on the same individual. And if I don't do anything, what GEE is going to assume is that these responses came from the same individual, the individual 1, and they didn't. So we have 65 individuals in group 1, and we have 48 individuals in group 2. An easy fix, so what I would like for these to be doing is continuing from 65. So I would like, instead of 1, I would like that to be 66, 67, ... And so an easy fix is to add 65 to all of these. So when I load in the data, first thing I do is say data where column 1 is equal to 2, replace its column 2 with its column 2 plus 65. Does that make sense? Sort of. You want the second column to go 1, 2, 3, 4, ... 65, 66, 67, ... all the way through the end. Once you make that change, then that issue has been addressed. There are missing values in these data. So there are missing data in the cholesterol data, also in the exercise data. GEE can handle missing data, so you don't have to do anything special for it. you're going to use a new function this time. It's the GEE-GLM function from the GEE-PAC package. That and the GEE package and its associated GEE function both do GEE. GEE-GLM, I can't remember why I preferred it here. It may be because I can then use the ANOVA function on it to test what we're going to test. But both of them basically do the same thing. I think GEE-GLM may be more actively maintained these days. Okay, for the first problem with the exercise data, there are missing values. Talked about this in last night's Q&A a little bit, but what you're going to do in part A is use ordinary least squares, IID regression, LM, to fit a model. That's the wrong model because it's not accounting for correlation. But we said in the notes that one way to explore the correlation structure is to take the residuals from that IID regression and compute correlations with them. In usual IID regression, if you go back to before correlated data stuff, we said there was a constant variance, sigma squared, that applied to every individual. And in order to do inference, to get standard errors, we had to estimate that little sigma squared because the variance of beta hat was that sigma squared x transpose x inverse. To get standard errors, I need to put a hat on sigma squared. And the way we did that in IID regression was to take the residuals from our model and basically compute a variance of them because the residuals contain information on variability, and now they're going to contain information on covariability, correlation covariance. So if you do IID regression on the exercise data, get the residuals, you can organize those residuals in the same way that the exercise data is organized, like in a wide format, where you have rows for individuals and columns for the repeat measurements on the same individual. So if you do that with the residuals, you have an n by p matrix of residuals. If you call the core function, COR, that computes a correlation matrix. So for the exercise data where you have repeat measurements over time, if you get the residuals, put them in that format, and do core, you'll get back, I don't remember how many time points there are, let's just say p. There's p time points. When you say core on the residual matrix, you'll get back a p by p correlation matrix. One's down the diagonal, and all the off diagonals are correlations. That's what is the target for part A. Do that, get that estimated correlation matrix, and then make an image of it using the heat map function. So I did that in last night's Q&A. Basically, a heat map is just a picture. In this case, if there's p time points, it's going to be a picture with p times p cells. So it's just an array of cells. And each cell is colored based on the number that corresponds to that cell. So you'll see visually and in color ones down the diagonal, and then numbers that are brighter or less bright depending on how strong all the little correlations are. So look at that picture, and what does it tell you about possible correlation structure? Structure means, what does the correlation matrix look like? Are all of the correlations different from all the other ones? In which case, maybe unstructured is the structure. Or does it look roughly like all the correlations are the same? In which case, a compound symmetric would make sense. Or does it look like the correlations are tapering off as you move away from the diagonal? In which case, an autoregressive would make sense. And then the other detail for this assignment is with the cholesterol data, we're going to learn Friday how to model time course in a curvy way. So if you think about what a time course might look like, say we have maybe our response is pain, and we're going to treat people with chronic pain with some drug, and then we're going to measure them over time. So at time 0, that's baseline, that's when we treat them, and then we're going to measure them at these time points, say. They come in with lots of pain. We give them the drug, and assuming it works, it lowers the pain, but then maybe it kind of levels off. You're not going to, yeah, so maybe it levels off. It's a non-linear time course. So suppose that is what we think is going on, or we want to allow for that to be going on. We made pictures early on, and it looked like maybe a nonlinear relationship. If I think it's a nonlinear relationship, then I don't want to say pain I equals beta 0 plus beta 1 time. That's not optimal because I don't think it's a linear relationship. And that model will do its best. It will fit a line. So it would fit something like that, which captures, the most of the trend, but it's not capturing all of the trend. So what might you do instead? One thing you could do is, instead of saying that the time course is linear, we could say it is, say, quadratic plus beta 2 times I squared plus epsilon I, in which case it will probably do a better job of capturing that trend. We could say quadratic, we could say cubic, we could say lots of different things. What we're going to learn about on Friday is how to say something pretty general and let the data decide what the form is. Maybe I don't really think it's quadratic, but I think it's curvy. So what we're going to do is models like this. Pain I equals beta 0 plus some function of time, where f is a smooth curve. And we will put limits on how smooth it needs to be by providing R with a certain number of degrees of freedom to use in fitting the function. So this is going to be what we call a spline. F is going to be called a spline, which has complicated details, but we don't need to know all the details in order to use it. I'll show you how to do it in R. Suppose we had data that looked like this, and we wanted to fit a curve to that. We could fit a line. The line would be kind of like that. We could fit a quadratic, a cubic. What we're going to do is fit what's called a natural cubic spline, which, roughly speaking, picks transition points on the x-axis, and in between those transition points fits a cubic polynomial under the restriction that it has to be continuous at each of those breakpoints. So it's it allows it to be flexible, like that. And then how many degrees of freedom can you use to do this allows me to limit how wiggly the function gets. I don't particularly want to interpret or interpolate the curve. That's a, quote, curve, but it's more wiggly than I would prefer. I think the true underlying structure is smoother, so by changing the number of degrees of freedom, if I were to say you only have 1 degree of freedom to fit this curve, it's going to fit the line because it only needs 1 parameter to fit that slope. If I say you have 20 degrees of freedom, it's going to interpolate the picture. If I say 5 degrees of freedom, it's probably going to do something sensible that's somewhere in between. So long story short, we're going to learn how to use natural cubic splines to flexibly model a time course. I think in all the examples, we're just going to use the default choice for degrees of freedom, which is 5. 3 or 5, I've seen that used a lot. At the end of the day, when you've done this, you have estimated the time course in a smooth way. And another thing that you could then do is suppose we have 2 comparison groups. So sticking with the pain example, pain and time. And maybe we fit, suppose we do a regression model. This is what you're going to do actually. Cholesterol data, there is a treatment group, and you are going to fit a correlated data regression model allowing for separate cubic splines for each treatment group. As in, we're going to allow for there to be a trend for treatment group and a trend for control group. To do that, we're going to say pain I is beta 0 plus f, a function for the treatment group of time, well, I'll show you in the R code. Basically, we're going to have a model that has treatment in it, treatment group, and time modeled as a spline, and an interaction between the two. So what that does is it says there's a time course, it's curvy, potentially, and there's an interaction with treatment group, which means there's going to be a separate time course for each treatment group. So it'll look something like GEE, pain, tilde, treatment, plus time, plus treatment, times time. And then all the options out here, correlation structure, ID. So then what you could do, you fit that model, you have some treatment that you're assessing for the pharmaceutical company, say, and you might ask, a scientific question would be, is there a treatment effect? How do you test, is there a treatment effect now? You have these 2 curves. What do you mean by, is there a treatment effect? So you could answer that in different ways. You could say, at the end of the time course, is the pain lessened by treatment? I should have organized these differently. Hopefully, it would go in this direction. So you could just look at the last time point and test, is treatment at the end in better shape than control at the end? If you did that, you'd kind of be ignoring some of your information because you didn't incorporate all the different time points when you answered that. You could fit this model, fit those curves, and use the curves as the basis of your assessment. In that case, you did use all the data to fit the curves, but then you just limited attention in your inference to that last time point. Could do that. Another kind of more general question, I guess, would be, are the time courses the same? Is the green curve the same as the blue curve in a statistically significant way? So how would you test that? what you could do, this is what you will do, is fit two models. So basically do an F-test. We have time, or we have treatment in the model. It's in there twice. We have a main effect, we have an interaction. These time pieces are a little more complicated because they're these splines. But roughly speaking, we just have a model with main effect for treatment and an interaction with time. So is there a treatment effect? The way we've answered questions like that so far is to do an F-test or a likelihood ratio test, because it's essentially asking, let's consider two models. Let's consider the unrestricted, which is the one we just wrote up there, pain, tilde, treatment, plus time, plus treatment, times time, options, and fit the restricted model, which is the model without treatment. So in order, that model would just be this one, where I've pulled out everything to do with treatment. And what you can then do to put a p-value on that comparison is an F-test. And R makes it easy for us. So in the homework, I said use the ANOVA function. ANOVA, if you have two nested models like ours, the restricted model is nested within the unrestricted model because it is the unrestricted model where we've just removed some terms. And the ANOVA function in R compares nested models and does an F-test. The p-value that would come out of that ANOVA call would be for the null hypothesis of no treatment effect. Okay. What else? I was going to do a couple of examples. Remind me which ones. Okay, so let me check scripts. There we go. Here's one example. Scripts. I want beat the blues. I want epilepsy. And what's the other one? Respiratory. All right. Let's start with epilepsy. Okay, so these data are from a randomized clinical trial, and it's about a drug for limiting epileptic seizures. So we have 59 patients, and they're randomized into control or treatment. Treatment got this drug called Progabide, and control got a placebo in addition to standard of care. And our response is the number of seizures in 2-week periods. We have 4 2-week periods. So we have 4 time points for each individuals. We also have a baseline seizure count for the 8 weeks before the study started. Okay. So let's load the data. They are in this package, HSOUR2. See if I have to install that. Install. So these data are correlated data. They're longitudinal data because we have 4 measurements over time on each person. Another interesting element of these data is that they are count data. These are number of seizures in each time period. So they are maybe not the right assumption to say that these are normally distributed data. Count data, a good starting point for what distribution applies to count data would be a Poisson distribution. Poisson is for number of events that happen over in a particular time period, like the number of calls that come into a 911 center in the next 2 hours. You might model that as a Poisson variable. So GEE is generalized in the sense that it can handle regression for responses that are not normal. Everything we've done so far has been with normal data, but if you've heard of, say, logistic regression or Poisson regression, that's regression, but with responses that come from non-normal distributions. Those are generalized linear models. GEE does generalize linear models while accounting for correlation. So I'm going to demonstrate how to do that. We are going to use this family argument now to say which distributional family do we have in mind. There's a handful that GEE can handle. Like binomial, it can do that. So it could do logistic regression with correlated data. By default, it assumes Gaussian or normal. That's what we've been doing without specifying anything. And there are some other options. Okay, so let's look at the data. (236 by 6). We have 59 patients, each of them measured 4 times. So that's where the 236 comes from. These data are apparently in long format. Subject 1, first 4 rows are for subject 1. Those are the 4 time points for subject 1. We have treatment group. We have baseline seizure count, which doesn't change with time because that was just a single measurement taken at the beginning of the study. We have their age, and we have the number of seizures in each of these 2-week periods. I'm just computing some summary statistics within each of the groups. So placebo group, time point 1, the mean number of seizures, is that right? That's a variance. The mean number of seizures in placebo group time 1 was 9.4. Placebo group time 2 was 8.3. Placebo group time 3. Placebo group time 4. So it doesn't look like much happened. Just looking at the means doesn't look like there's much of a trend in the placebo group. In the treatment group, started at 8.6, went down a bit to 8.4, went down a bit more to 8.13, and went down a bit more to 6.7. And then these are variances. And I'm going to fit the code. I'm not going to go through all the code, but it includes the first 2 models are GLM models. Those are generalized linear models. That's like IID regression, except where we're not working with normal data. So I could do GLM to do a usual Poisson regression or a usual logistic regression. So I just included those as an illustration of what GLM looks like. I would not use those models in this example because GLM is not doing anything about correlation. But GEE is. So let's fit a GEE model and see what it looks like. I fit a GEE model using a working correlation structure assumption of independence. We know it's not independent data, but we've said in the notes that GEE is okay with us getting it wrong. It can give us valid standard errors even if we get this wrong. Okay, and then we have our model estimates, a baseline effect which says statistically significantly that more baseline seizures are associated with more after the study started, which kind of makes sense. So if you're tending to have more seizures, you're going to tend to have greater than average seizures after the study starts. Age has a very borderline, statistically significant positive association. Older you are in this study, the more seizures you tended to have. And then here's the treatment effect. We modeled treatment effect, right, so treatment effect. This is 0-1 categorical variable, placebo or treatment. And there is a negative association. It seems to, on average, decrease the number of seizures, but it is not statistically significant. So I'm just looking at that statistic at the end. Remember that GEE doesn't give us p-values. I could compute a p-value, but I know roughly that 2 is the magic number for these statistics. Any statistic value that's bigger than 2 or less than -2 is going to have a p-value less than 0.05. So this guy is not statistically significant. Another example. Beat the Blues. So this is an interesting study. Longitudinal data from a clinical trial, and the target population was depressed people. There was a treatment group and a control group. Control group is treatment as usual, with, I don't know what that is exactly here, counseling maybe an antidepressant. And the treatment group got that and a DVD, basically is what it sounds like. They got a multimedia program called Beat the Blues that was supposed to give you behavioral therapy. So treatment versus control, longitudinal data. Let's load the data in. Looks like I'm going to have to install another package. Beat the Blues. 100 by 8. And here's what the data looks like. I don't have details on these variables. They're in the book, I think. The the Regression and Applications in Biostatistics book. But we have, I assume, actually I could just do question mark beat the blues and it will tell us no documentation. Maybe not. Something called drug. I guess that's I guess maybe that's, are you taking an antidepressant? If I had to guess, that's what I'm guessing. Are you on an antidepressant? Length, not certain what that is. Here's treatment group, treatment as usual versus the multimedia program. And then here's all of the response values, which are some assessment tool for quantifying how depressed you are. Bigger numbers correspond to more depressed, and there are some missing values. Okay, making a picture here. Let me just make the picture and comment on it. Side-by-side box plots by treatment group. So here is the control group. Depression symptoms looking like they went down over time, roughly. Here is the treatment group. Y-axis is the same. The scale is the same on both sides. And qualitatively comparing the two, looks like the treatment resulted in a more pronounced decrease in depression symptoms. The pattern seems to drop down more rapidly, and it achieves a lower level. So on average, at the end of the time course, depression was under 10. On average, after the time course in the control group, it was still above 10. So just based on the picture, it looks like there is a treatment effect. Let's do GEE. To do GEE, the data are in long or wide format, one row per individual. In order to do GEE, I need it to be in long format. So I need one column containing all the response values, and then a column for identifying repeat measurements on the same individual. That's what GEE wants. So I'm going to reshape the data, and I did this in the Q&A last night too. So let's create a new version that's reformatted, and I'm going to use the reshape function to do that. So reshape allows you to go from long to wide or from wide to long. We want to go from wide to long. So reshape the Beat the Blues data, and the direction I would like you to go is long. Best way to learn how to use the arguments is by example. If you look at the help file for reshape, it's I think a little bit hard to figure out what you're supposed to do with those arguments. But in the Q&A and also in the solutions to homework 6, I showed examples of going both ways, from wide to long with the orthodont data, and then from long to wide with the orthodont data. So you can mimic that code. This is going to give us a new version of our data set. We now have 400 by 7. Looks like this now. And so there's a new column called subject, there's a new column called time, and there's a single column for the response called BDI. And that first row is the first time point for individual 1. Second row is first time point for individual 2, and so on. Okay. So notice that the subjects aren't organized in chunks. When I did reshape, there might be a way to use the arguments to make it perform differently, but what it did by default was put all the time 2 measurements followed by all the time 4 measurements followed by all the time 6 measurements and so on, which means that individual 1 is spread out among things. So all I did in this command is pull out only the data for the first 3 individuals just so we can see what's going on. At the time I wrote this, I was under the impression that GEE expects the individuals to be clumped together, not like they are right now. And I'm not certain that's the case, but I'm going to go ahead and do it. I'm going to reorganize the data again to make it so that the first 4 rows are all subject 1, followed by the next 4 rows subject 2, and so on. So here's doing that. I'm going to order the subject identifiers from least to greatest, and then I'm going to reorganize the rows to match that. Looks like this. Now I have subject 1, 1, 1, 1, followed by the next one, and followed by the next one. So now let's do GEE models. These are, let's say, normally distributed data. I mean, they're not really count data. They're not count data. They're integers. Maybe they're not truly normal, but that seems like the most natural choice. So let's assume normality, and let's fit this model. We're going to have a term for baseline, BDI pre. Yeah. Baseline depression. And we're going to have a term for treatment group, factor, categorical, a term for length, and a term for drug. So again, I'm not certain what length and drug are, but we're just going to include them in the model. Okay, what do we get? That particular model, I assumed independence, and I'm going to rely on the robust standard errors from GEE. Here's the output. We have a statistically significant baseline effect. We have a marginally significant drug use effect. And not quite statistically significant, but promising treatment effect. So treatment is 0 or 1, depending on whether you're control or beat the blues, respectively. And what the model is saying is that treatment group tends to have lower depression. And it's marginally statistically significant because its test statistic is nearly -2. If it was bigger than 2 or less than -2, I would say p-value less than 0.05, and it's close. Okay. And there was one other example that I was going to do. We don't have time to go through it in detail, but I'll just show it to you. Another time course example, respiratory status of patients in a randomized clinical trial. Patients randomly assigned to treatment or control. And during the treatment, the response is respiratory status, and it's categorized as either good or bad. So it's not a number. It's not, this is logistic regression because you're either 0 or 1, basically. 0 for poor, 1 for good. And I want to model that, like the probability of being good, in terms of covariates. That's logistic regression. We have 4 time points, and we have 111 observations. Okay, so let's load in the data and have a peek, and then I'll just run a model and we'll finish. $555. And we have 5 time points. Is that what we said over here? 4 time points. Maybe I was wrong. There's a baseline and then 4 time points after the beginning of study. Let's fit a model. I'm going to set aside the baseline variable, and then let's just fit a model. So this is different from what we've done so far because of the nature of the response variable. It is binary. You either are in good condition or you are not, which means I want to do logistic regression. So the family that I chose when I did GEE was the binomial family. Binomial is for 0-1 outcomes, success, fail, flipping a coin type thing. But then what you get is very familiar stuff. You get estimates and standard errors and statistics. So if we have time, we'll talk a little bit about how to interpret the results of, say, logistic regression, because it is a little bit different. In IID or in usual regression, coefficients are mean change associated with a 1-unit increase in that covariate, holding everything else constant. Logistic regression is a little different. It's a log odds ratio associated with a 1-unit increase in the covariate, holding everything else constant. So the interpretation is a little more cumbersome. So what do we have here? We have center treatment group looks statistically significant. In the treatment group, you have better chances of being in good shape. Coefficient's positive, it's increasing the odds of being in good shape when you are in the treatment group relative to the control group. There is a strong statistically significant effect of the baseline status, and that's mostly it. Okay, so that's all I wanted to say with those examples. 3 examples of using GEE to do correlated data regression for longitudinal data, and the one take-home message is that GEE allows you to do generalized models. If you have count data, consider a Poisson regression. If you have binary, success, fail, alive, dead, data like that, consider logistic regression. Okay? Questions? Friday, we will talk about how to do the spline stuff. So I'll show you a couple of examples, and yeah, I'll show you some examples. Okay, see you Friday.